So inverse trigonometry tends to be a topic where students think they're learning something completely new and different. That's a separate idea from trigonometry, and it sometimes comes off a little scary. So I want to approach this conversation in a way that maybe makes you feel a little bit more comfortable with it. So when I have you thinking about inverse trig evaluations, essentially, I just want you to think about going backwards from what we were doing when we were evaluating trig functions at special angles. Okay, so for example, when we want to find the sine of an angle, we go to the y value on the coordinate at that angle. And when we want to find the cosine of an angle, we go to the x coordinate, right? And I'm going to stick to sine and cosine for this conversation. Okay, so, we have these ratios, 1/2, right? Radical 3/2, radical 2/2. These ratios are the sines or cosines of each of these angles here, right? So what is the inverse trigonometric evaluation? What are we doing? We're going backwards, okay? So, a lot of times when we pose the question, what is the inverse sine of radical 3/2, a student will say, oh my gosh, how am I supposed to memorize that and all of the other things I'm supposed to memorize? Well, again, instead of memorizing, let's just think about what we know. All right, and I think almost everybody at this point has got the first quadrant of the unit circle under wraps, right? We've got that figured out. And not necessarily memorized, but you've worked with it enough where it's kind of fresh there and, on the tip of your tongue, ready to come out. So, this would have been the way we asked the question in a high school class. What is the inverse sine of radical 3/2? What the heck does that mean, right? Well, really what that's asking, same question, different wording, is at what angle is the sine, not the inverse sine, but the sine equal to radical 3/2? Because I know how to answer that question, right? Basically, what this is asking for is the inverse sine of radical 3/2, which is an angle. I'm going to call it theta. The inverse trigonometric evaluation of a ratio is an angle. These are angular measures. Okay. So basically, again, what I'm looking for is the sine of what angle theta is radical 3/2. Well, that's easy. I'm just going to go over here and find my y because sine is y. I'm going to find my y value where radical 3/2 is what we have. And here it is. And that is at the angle pi/3. So the sine of pi/3 is radical 3/2. Right? I think we can all agree that the sine of pi/3 is radical 3/2. So the inverse sine of radical 3/2 is pi/3. I'm just going backwards. I'm just reversing the direction. Okay, and that's what inverse functions do. Okay. So if I want to ask for, and I'll leave this up here for a minute. I do have a bleed through paper though, because markers that I have left are a little bit heavy. Okay, so I'm going to leave my unit circle up here and let's go ahead and look at the inverse sines of these three ratios. So essentially, again, what I'm looking for is what is the angle theta where the sine of theta is equal to 1/2. Okay, so let's go ahead and look for our y value because don't forget y is sine. Let's look for a y value of 1/2, and here it is at the angle pi/6. So the inverse sine of 1/2 is pi/6. Okay, let's do the next two without having to show much work, okay? Because this is helpful for you to understand it, but it's a lot of extra writing and maybe not quite so efficient. All right, so again, instead of saying what is the inverse sine of radical 3/2, let's ask the question, at what angle is the sine equal to radical 3/2? Okay, so we're going to look for that y value of radical 3/2. Here it is. And that's at pi/3. Okay. And I'm sticking to the first quadrant for today, just to make sure that we're able to understand what we're being asked. All right. New videos coming up. We'll talk about other aspects of inverse trig and where else we can be looking for these things. All right, radical 2 over 2. Let's see, the y value needs to be radical 2 over 2 because the sign is the y value. So when is the sign equal to radical 2 over 2? Here it is, at pi over 4. So we're asking the same questions we asked before, but in a different order. Instead of me saying, what is the sign of pi over 4? Well, the sign of pi over 4 is radical 2 over 2. Now I'm saying, when is the sign equal to radical 2 over 2? At pi over 4. All right, so let's go ahead and take a look at our cosine evaluations that I wanted to do. So now we are looking for the x values, right? Because cosine is x. All right, so at what angle is the cosine equal to radical 3 over 2? So I look for my x value of radical 3 over 2. Here it is, at pi over 6. So the inverse cosine of radical 3 over 2 is pi over 6. Because the cosine of pi over 6 is radical 3 over 2. All right, now I'm looking for the inverse cosine of a half. So now I'm looking for the x value to be 1/2. Okay, and I see that right here. And that occurs at the angle pi over 3. Again, that's because the cosine of pi over 3 is 1/2. All right, and then lastly, I'm looking for the cosine to be equal to radical 2 over 2. So the inverse cosine of radical 2 over 2, here it is, x is radical 2 over 2. That's at the angle pi over 4. Okay. So I'm just going to go in with a different color really quickly and rewrite basically, this statement, but rearranged in a different color. And I'm going to stick to the cosines for now. But basically what we're saying here is that if the inverse cosine of radical 3 over 2 is pi over 6, that's because the cosine of pi over 6 is radical 3 over 2, which we knew. And we also know that the cosine of pi over 3 is 1/2. So I'm reversing the order. Okay, and then down here, right, we know that the cosine of pi over 4 is radical 2 over 2. So again, these are kind of the same relation, but it's just in what direction am I looking? Okay, so that's how we want you to think about it. It's not new. It's not a new conversation. It's a new way of having the conversation. Okay. So there's another way to look at this with right triangles. Okay, and I'm actually going to hold off on what's down here. So try to ignore that for a moment. I was just trying to prep my spacing. So let's say I have a triangle with an x, a y, and a hypotenuse of 1. So legs of x and y and hypotenuse of 1. Okay, and I want to formulate the sine, cosine, and tangent of the angle theta that I've placed down here in the bottom left. So if you remember with the right triangle trigonometry, we had that acronym SOHCAHTOA. And that helps us remember that sine of an angle theta is opposite over hypotenuse. So we can write this as y over 1 or just y. Right? Opposite over hypotenuse, which I did this on purpose because I want to remind us that sine is y in the coordinate on the unit circle. All right, and then cosine would be adjacent over hypotenuse. So x over 1, which is just x. And then tangent would be opposite over adjacent, so y over x. And don't forget, that's the same thing as saying rise over run, which is slope, right? And tangent we think of as meaning slope of something. Okay. But now what I want to do is look at how I can write these relationships in terms of the inverse trigonometric functions. So I've started talking about them here. I haven't actually finished writing them. So let's say I want the inverse sine of y. Okay, so I'm coming back up to this first expression here, the inverse sine of y. Okay, that would be equal to theta. Okay. If I wanted the inverse cosine of x, that would also be theta. All right, and then the inverse tangent of y over x, well, that is also theta, which means I can write this angle theta in terms of actually not just 3 inverse trigonometric functions, but 6, because we could potentially, which we won't do often if we do at all, look at inverse cosecant, inverse secant, and inverse cotangent. Okay, but here's the point. If I'm looking at this right triangle, I can visualize theta as the inverse sine of the opposite side, y. I can visualize it as the inverse cosine of the adjacent side, x. Or I can see that theta is the inverse tangent of the rise over run y over x. It's, again, there are 3 other options that we could be looking at, but those won't be considered as often, if at all. So the angle represents the inverse trigonometric function of the ratios of sides and hypotenuse. Okay. So again, what we were looking at over here at the very first, part of this video, the inverse trigonometric function is the angle. It's an angular measure. Okay. So there's only one other thing I wanted to do in this video, because I did want to keep this one short and make sure that we weren't going too overboard. I wanted to make sure that everybody saw the other notation that we can use for this. Inverse sine can also be written as what's called arc sine. So this says arc sine of y. That is the same thing as inverse sine of y. Okay. And same thing down here. This can be written as arc cosine of x. And here we could write this as arc tangent of y over x. What's really important to know is that inverse trigonometric functions are not the same thing as raising a trig function to a power. That is not the same thing. Okay, you're not raising sine to the negative first power. So in other words, if you think about the fact that sine to the negative first is 1 over sine, and 1 over sine is cosecant, the common misconception is that inverse sine is equal to cosecant. That is not true. So we want to make sure that we're very careful in stating that, this is an angle, whereas this is a cosecant of an angle. Those are not the same thing. Okay. All right, so as long as we have that down, that's a nice preliminary video to inverse trig. Again, all we're saying is let's reverse the way we ask the question that we've been asking for several weeks now. Okay, instead of asking what is the sine of an angle, we're asking at what angle is the sine equal to the ratio in question. Okay, so we're just going backwards.